Tonight, we're going to explore something that seems quiet and invisible, but is actually one of the most amazing mysteries on our planet: hidden worlds beneath the ocean floor. You've probably seen the ocean many times, on maps, in photos, or on documentaries. Scientists study it constantly when they talk about Earth's depths. But here's what most people don't realize. When you truly begin to understand what lies beneath the seabed, when you grasp the mountains, valleys, and secret life that exist far below the waves, it changes how you see our oceans. This is not just empty sand and rock. It's a world so vast and complex that it challenges our ideas of life, geology, and the unknown. And by the end of this journey, you're going to understand exactly why exploring these hidden places matters and why much of it remains a mystery even today. Before we go any further, if you enjoy slow, deep explorations like this, a quick like or subscribe really helps the channel grow. It's a small thing for you, but it makes a huge difference for me. Now, let's begin. For most of human history, the ocean floor was treated as a final line. It was the place where water ended and nothing else could be reached. Sailors crossed the surface and guessed at the depth below, but what lay beneath the waves was not part of daily thought. The deep ocean felt distant, heavy, and sealed off. Maps showed blank blue space. Depth was measured with rope, not with clear sight. The bottom was assumed to be flat, dark, and still, a silent end to motion. This idea stayed strong even as science grew. Early ocean study focused on surface water, tides, and coastlines. The deep sea was hard to reach and easy to ignore. Pressure crushed early tools. Darkness blocked vision. Cold slowed machines. Each layer of water added weight that humans could not feel from above. The ocean floor became a place defined more by limits than by detail. It was easier to imagine it as empty than to accept how little was known. Yet the ocean floor is not an end. It is a boundary. It is the thin line where water meets rock, and where forces from inside the earth meet forces from the sea above. This boundary stretches across most of the planet. More than 2/3 of Earth's surface lies under ocean water, and nearly all of that water rests on solid crust. The ocean floor is not rare or distant. It is the most common surface on Earth, even though few have seen it directly. The pressure at the seafloor is steady and strong. For every 10 meters of water, pressure increases by about 1 atmosphere. At depths of several thousand meters, the weight of water presses down with a force that can crush steel not made for it. This pressure shapes everything below. It slows motion. It changes how rocks crack. It affects how fluids move through tiny spaces. The seafloor exists under a constant load that never lifts, day or night. Light fades fast in water. Sunlight weakens after the first few dozen meters and vanishes long before the deepest parts of the ocean. By the time the seafloor is reached in most places, there is no natural light at all. Darkness is complete. Yet this darkness does not mean absence. It means that energy and change follow rules that do not depend on the sun. The seafloor works on heat from within the earth, on chemical flows, and on slow physical motion. Temperature near the ocean floor is often close to freezing. Cold water sinks and spreads, forming vast deep currents that move across entire ocean basins. These currents brush the seabed and shape it over long time spans. Fine particles settle, coarse grains stay put. Over years, centuries, and millions of years, layers build up. The floor is not smooth. It holds hills, valleys, ridges, and wide plains shaped by gravity and time. For a long while, humans assumed the seafloor was mostly still. Mountains and valleys were thought to belong to land. The deep ocean was seen as flat by default. This belief came from lack of evidence, not from proof. Without clear images, the mind filled gaps with simple shapes. Flat surfaces are easy to imagine. Complexity takes data. The shift began when sound replaced rope. By sending sound waves down and listening for echoes, scientists could measure depth with far more reach. These early soundings showed that the seafloor rose and fell. Depth changed often. Some areas were shallow. Others dropped suddenly. Long chains of underwater mountains appeared where none were expected. The ocean floor was no longer a blank. It had form. As sound tools improved, patterns emerged. Long ridges ran through the centers of oceans. Deep trenches cut along their edges. These were not random. They followed rules that hinted at deep motion below the crust. The seafloor began to look less like a resting place and more like a moving skin stretched over a restless planet. The idea of a boundary became clearer. The ocean floor is where water pressure meets rock strength. It is where heat from inside Earth leaks into the sea. It is where chemical exchange happens at a slow but steady pace. Seawater seeps into cracks. Minerals dissolve and reform. Gases move up and down. The boundary breathes, though not in a way humans can feel. This boundary also marks a change in time. On land, wind and rain reshape the surface quickly. Rivers cut valleys. Plants break rock. On the seafloor, change is slower in some ways and faster in others. There is no wind, but there are currents. There is no rain, but there is constant settling of particles. A thin layer may take thousands of years to form, yet a sudden slide can reshape a slope in minutes. The ocean floor holds memory. Each layer of sediment is a page written by the sea above. Dust from deserts drifts down. Shells from tiny sea life fall and break. Ash from distant volcanoes settles in thin sheets. Over time, these materials stack in order. Older layers sink deeper. New layers cover them. This slow record tells stories of climate, ice, heat, and life far above the seabed. Seeing the ocean floor as a boundary also means seeing it as active. It is not a dead base. It moves with the plates of the earth. Large sections of the seafloor are created in some places and destroyed in others. New rock forms where molten material rises. Old rock sinks where plates meet and bend. This cycle happens far from human sight, yet it shapes the planet's surface and oceans alike. The water above responds to what happens below. Heat from the crust warms deep water in certain regions. Gases released from rock alter ocean chemistry in small but steady ways. The shape of the seafloor guides currents, steering cold water through narrow paths and wide basins. The floor controls flow as much as the water controls erosion. Standing on a ship, the ocean looks flat and endless. The surface hides depth so well that it feels calm and simple. Yet below that surface lies a world of structure and force. The ocean floor is not a distant bottom. It is a vast hidden skin, active and complex, holding together water, rock, heat, and time. Understanding this changes how the planet is seen. Earth is not just land with water poured on top. It is a system where the largest space is hidden from view. The seafloor connects the deep earth to the moving ocean. It links slow rock cycles with flowing water above. It forms the stage on which unseen processes play out every moment. The idea of an end gives way to the idea of connection. The ocean floor is not where things stop. It is where many processes begin, pass through, and continue onward. It is a place of meeting, not of silence. Beneath the waves, the planet remains active, shaped by pressure, heat, and motion that never rest. To understand what lies beneath the ocean floor, Humans first had to accept a simple fact. Eyes are useless there. Light cannot reach the depth where rock begins. Cameras see only darkness unless they carry their own lamps, and even then, they show only the surface. Everything below the seafloor must be sensed in other ways. The main tool became sound. Sound moves well through water. It travels far, bends slowly, and reflects when it meets a hard surface. Long before clear images were possible, scientists learned to send sound downward and listen for its return. A pulse would leave a ship, pass through the water, strike the seabed, and bounce back. The time it took to return revealed the depth. This was the first step in turning the invisible into something measured. Early sound maps were rough. They traced only simple depth lines. Valleys and hills appeared as numbers, not shapes. Still, these early maps changed thinking. The ocean floor was uneven. Some areas rose high, others dropped sharply. Depth changed over short distances. The idea of a flat bottom faded as more soundings filled the gaps. As tools improved, sound was used in more complex ways. Instead of a single pulse, wide fans of sound were sent out. These fans scanned broad strips of the seabed at once. Ships moved, back and forth, laying down lines of data like threads on cloth. Slowly, shapes formed. Ridges, plains, slopes, and scars became visible in outline. But the seafloor surface was only part of the story. Below it lay layers of sediment and rock, hidden from direct view. To see these layers, scientists used stronger sound pulses that could pass through the seafloor before reflecting back. These waves moved through soft sediment, slowed or bent, then bounced off deeper boundaries. Each echo carried clues about what it had touched. This method revealed that the seafloor is layered like pages in a book. Soft material rests on harder rock. Some layers are thin and smooth. Others are thick and uneven. Breaks appear where motion or pressure change the structure. These layers record long histories of movement, build-up, and change. Interpreting these echoes is not simple. Sound does not return as a clear picture. It returns as signals that must be translated. Speed changes depending on the material it passes through. Water, mud, sand, and rock each affect sound differently. Scientists compare patterns, shapes, and timing to build a picture that makes sense. Much of this work relies on careful testing and slow comparison, not quick answers. Gravity also plays a role in mapping the unseen. The pull of gravity is not equal everywhere. Dense rock pulls slightly more than lighter material. As ships pass over the ocean, small changes in gravity can be measured. These changes hint at what lies below. A heavy ridge buried under sediment may tug a bit harder. A deep basin filled with lighter material may pull less. These signals are faint but steady. By combining sound and gravity data, scientists gain more confidence. When both methods suggest the same structure, the picture becomes stronger. When they differ, questions remain. The ocean floor below the surface is often mapped through agreement, not certainty. Each method fills gaps left by the others. Even with these tools, limits remain. Sound spreads as it travels. Fine detail blurs with depth. Thin layers may blend together. Small features can vanish in noise. The deeper the target, the less clear the signal. Beneath thick sediment, the view grows softer, more open to guesswork. Maps become smoother, not sharper. Time is another limit. Mapping the ocean floor is slow. Ships move at steady speeds. Fuel, weather, and cost restrict coverage. Much of the ocean has been mapped only once, with older tools. Some regions remain known only in broad strokes. High detail maps cover a small part of the total sea floor. Data also comes in pieces. Different teams use different tools at different times. Some areas are scanned in detail for research or safety. Others are crossed only in passing. Bringing all this data together takes effort and care. Old records must be corrected. New data must be matched to existing maps. Errors must be found and fixed. Over time, global maps have grown clearer. Large features are now well known. The main ridges, deep trenches, and wide plains stand out clearly. Yet between these major forms lie countless smaller shapes that remain unseen. The ocean floor is vast. Even with modern tools, much of it remains suggested rather than shown. Despite this, the progress is steady. Each survey adds detail. Each new tool sharpens the view a little more. Better sound control improves clarity. Better motion tracking reduces blur. Better models help translate signals into form. The unseen becomes less unknown, layer by layer. The act of mapping also changes how questions are asked. Early explorers wanted to know how deep the ocean was. Later scientists asked why it was shaped the way it is. Now, attention turns to what lies beneath the surface and how it moves over time. Maps no longer serve only as guides. They become records of active systems. What remains hidden is not ignored. Instead, it is marked by uncertainty. Scientists know where data is strong and where it is weak. Blank areas are noted, not filled with guesswork. This honesty keeps the picture flexible. As new data arrives, old ideas can shift without collapse. The ocean floor below the seabed is still mostly unseen, but it is no longer untouched by study. Through sound, gravity, and patient work, a rough image has formed. It is an image built not from sight, but from motion and response. A picture drawn by echoes and pulls, shaped by careful listening rather than light. This way of seeing requires trust in indirect signs. It accepts that knowledge can grow without full clarity. The hidden world beneath the ocean floor is revealed slowly, not all at once. Each signal adds a line. Each survey adds depth. What remains invisible today may become clearer tomorrow, as tools improve and maps continue to grow. Beneath the ocean floor, the first hidden world is made not of hard rock, but of layers that drifted down from above. These layers are sediments. They begin as small pieces, almost weightless on their own. Dust from land rides the wind and settles on the sea surface. Tiny shells form in the water as small life grows and dies. Bits of rock break from coasts and slide down slopes. Ash from distant eruptions falls through the air and sinks slowly. All of this moves downward, guided by gravity, until it reaches the seabed. Once these particles arrive, they do not stop. They spread, roll, or sink into place depending on size and shape. Heavy grains settle fast. Fine dust can stay suspended for a long time before touching bottom. Water currents sweep some areas clean and pile material in others. Over long periods, this quiet motion builds layers that cover the ocean floor like thin blankets. Each layer rests on the last, adding weight, but also adding record. Time is written into these layers without words. The deeper a layer sits, the older it is. New material always arrives on top. Old material sinks and hardens under pressure. This order is rarely broken. Because of this, sediments act as a steady clock. By reading the depth and content of each layer, scientists can trace change across long spans of time. The rate of sediment build is slow. In some parts of the deep ocean, only a few millimeters form in 1,000 years. In other places, near rivers or slopes, layers grow much faster. These differences matter. Thick stacks of sediment point to long supply or strong flow. Thin layers suggest calm water or distance from land. The ocean floor becomes uneven, not just in shape but in history. Within the sediment lie tiny remains of life. These are not bones or shells large enough to see with the eye. They are small, simple forms that once floated in the water. When they died, they sank. Over time, their shells collected in vast numbers. Though each one is tiny, together they fill layers that stretch across whole oceans. Their shapes and makeup change, with water temperature, salt level, and available food. By studying these remains, scientists learn about past oceans. Some forms thrive in warm water, others prefer cold. Some appear when nutrients are high, others fade when conditions shift. When these patterns change through the layers, they mark shifts in climate. The ocean floor keeps this memory even when the surface world forgets. Chemicals also settle into sediments. Some come from the water itself. Others rise from below. Ratios between certain elements shift with temperature and ice cover. Small changes in these ratios can point to large changes above, such as the growth or loss of ice sheets. Even without visible signs, the chemistry tells a quiet story of Earth's past states. Sediments do not rest on a fixed base. The crust below them moves. In some regions, the ocean floor spreads apart slowly. New rock forms and sediment has little time to pile up. These areas tend to have thin layers. In other places, the crust sinks or stays still for long periods. Sediment gathers there, growing thick and heavy. Over millions of years, this difference can reach thousands of meters. Currents shape sediment too. Deep water flows are slow but strong enough to move fine material. They carve channels, smooth hills, and build long ridges of mud and sand. These features do not form in a moment. They grow grain by grain. Their shape reveals the path and strength of water that no human has ever seen directly. Sediments are often treated as dead matter, but this view misses much of what happens within them. Water flows through tiny spaces between grains. Gases move up and down. Heat passes slowly from the rock below. In these spaces, life can exist. Small organisms live within the sediment, feeding on chemicals and each other. They move slowly, dividing rarely, but they persist. Pressure increases with depth, squeezing the layers tighter. Water is pushed out. Particles lock together. Over long spans, loose sediment can turn into solid rock. This process does not erase the record, it seals it. The order remains even as form changes. What was once soft mud becomes stone, still holding signs of the past. Disturbance does happen. Slopes can fail. Earth movement can shake layers loose. Large slides can drag older material over younger layers, folding time. These events leave clear marks. Broken layers, mixed zones, and sharp edges stand out when scanned. They mark moments of sudden change against a background of slow build. Drilling into the ocean floor allows direct study of these layers. Long tubes of sediment are pulled up, keeping their order intact. Each section is logged, tested, and stored. Colors shift with depth. Grain size changes. Chemical makeup varies. Together, these cores act like long timelines pulled from the Earth. No single core tells the whole story, but many cores, spread across the oceans, form a network of records. When compared, they reveal patterns that stretch across the planet. Warm periods appear in many places at once. Cold phases show up in layers far apart. The ocean floor links distant regions through shared history. Sediments also respond to what happens below them. Heat from the crust can change chemical reactions. Gases rising from deeper rock can collect within layers. In some places, These gases form solid compounds under pressure. In others, they escape slowly, leaving paths behind. The sediment adjusts, shifts, and reacts. Because of this, sediment layers are not frozen. They continue to change even after burial. Slow reactions alter minerals. Life moves through tiny pores. Fluids migrate. The archive remains readable, but it is active, not sealed. It holds memory while still participating in the present. Seen this way, the ocean floor is not just rock covered by dust. It is a living record, written one grain at a time. Each layer carries signs of water above and heat below. Together, they form a deep memory of Earth, kept quiet by darkness and pressure, waiting to be read with care. Beneath the layers of sediment and the water above, the ocean floor moves. It is not fixed in place. The rock itself is divided into vast plates. These plates float on a softer layer below. They shift, slowly but constantly. In some areas, plates pull apart. In others, they collide. Sometimes they slide past one another. These movements shape the seafloor and the crust beneath. Where plates pull apart, new rock forms. Magma rises from below, filling the gap. This process occurs along long underwater mountain chains called mid-ocean ridges. The ridges stretch for thousands of kilometers across the oceans. They are the source of new oceanic crust. As magma cools, it becomes solid rock. This rock then spreads outward from the ridge, carrying the seafloor away like a conveyor belt. The creation of new crust is not uniform. Magma comes in pulses. Some areas grow faster, others grow more slowly. The rate of growth depends on heat from the Earth's interior and the movement of the plates. In some places, the ridge rises sharply. In others, it forms gentle hills. The shape of the ridge reflects how fast material emerges and how it interacts with water above. Not all plates move smoothly. Between sections of ridges, transform faults appear. These faults are cracks where plates slide past one another. Movement here is horizontal rather than vertical. The rock can grind, creating friction. These zones are important because they release stress and shape the sea floor. Earthquakes happen along these faults, even though they lie deep underwater. The process is slow and constant, invisible from the surface. At the edges of oceans, plates can meet and bend downward. This occurs at subduction zones. Here, one plate sinks beneath another into the mantle. The descending plate carries rock, sediment, and water with it. This process recycles the crust. Old rock disappears from the surface. It moves down into hotter layers, eventually melting. The cycle of creation and destruction keeps the ocean floor in motion and prevents it from remaining static. Heat from Earth drives all of this. The mantle beneath the crust is hot. It rises toward areas of lower pressure. At ridges, this heat melts rock, forming magma. In subduction zones, heat and pressure change sinking rock, releasing water and gases. The energy moves upward, affecting the crust and even the water above. Heat flow is slow but steady, shaping the movement of plates and the creation of new sea floor. Magma movement beneath the ocean is invisible, but its effects are clear. As molten rock solidifies, it pushes older rock outward. Layers of new crust grow. The magnetic minerals in the rock align with Earth's magnetic field at the time of formation. This creates stripes of magnetism that alternate across the seafloor. By studying these stripes, scientists can track the rate and direction of crustal spreading over millions of years. Crustal recycling is essential for the planet's balance. Without subduction, the Earth would accumulate too much crust at the surface. Without new crust forming at ridges, oceans would shrink. The cycle allows the surface to remain dynamic. It moves slowly, on a scale of centimeters per year, but over millions of years, it reshapes continents and basins. The ocean floor grows, ages, and is replaced in a constant rhythm. Most tectonic action happens beneath oceans. On land, faults and earthquakes are obvious. Underwater, movement is hidden by kilometers of water and sediment. Most of Earth's crust lies under oceans. Therefore, the majority of plate creation, sliding and destruction occurs where humans cannot see directly. It is a secret engine of the planet, operating quietly beneath the waves. The interaction of plates affects everything above them. Ridges push up mountains on the seafloor. Subduction zones form deep trenches. Transform faults produce small offsets in otherwise smooth plains. These features guide currents, trap sediments, and shape habitats. Even life on the seafloor depends on the underlying movement of rock. Volcanoes on the ridge feed chemical-rich fluids that nourish unique ecosystems. Tectonic plates are flexible but strong. They bend slightly under pressure, crack, and sometimes collide violently. Earthquakes underwater are different from those on land. Water above adds weight and dampens small motion. Yet large shifts can displace enormous volumes of rock and sediment. These events can create waves that travel across oceans and change the shape of the seafloor in minutes, though most change is gradual over millions of years. Over time, seafloor spreads. New rock moves away from ridges. Sediments accumulate on top. Water pressure compresses layers. Older crust becomes colder, denser, and more stable. Eventually, the crust may sink into a trench, completing its journey. This movement records the history of Earth's interior, even without human observation. Each meter of seafloor carries the story of heat, pressure, and motion. The process is ongoing and unstoppable on human timescales. Plates will continue to move, collide, and separate. Mid-ocean ridges rise, transform faults slide, and subduction zones consume crust. Magma will still push upward, slowly building new mountains below the waves. Heat will continue to flow from deep inside the planet. The ocean floor is not static. It is a vast, unseen engine driving change. Mapping these processes requires careful observation. Scientists track seafloor spreading by measuring the distance between magnetic stripes. They monitor earthquakes along faults. They study the chemicals in hydrothermal fluids at ridges to understand the movement of magma below. Each method provides a piece of the puzzle, revealing the hidden life of tectonic plates beneath the ocean floor. The pattern is global. Every ocean shows the same cycles. New crust forms in the center. Old crust disappears at margins. Plates move in all directions, creating a shifting mosaic. The scale is immense. Entire continents ride on these plates, moved imperceptibly by forces hidden below the waves. The ocean floor is the surface of a machine that operates out of sight. Even small details matter. A ridge may have small valleys and hills that influence currents above. A subduction zone may tilt sediments, guiding flow and deposition. Microplates and fractures add complexity. Each feature is part of a network of forces. The ocean floor is not flat, not uniform, and not inert. It is active and dynamic, built by heat, pressure, and motion. The movement of plates explains much about the ocean's shape and history. Ridges show where new crust has formed. Trenches mark where crust disappears. Patterns of earthquakes trace plate boundaries. Sediments align with slopes and currents influenced by tectonic form. The ocean floor is a record of both creation and destruction, written in rock and reinforced by pressure and time. Because most of this happens underwater, it remained hidden until modern study. Submersibles and sonar reveal surface forms. Magnetic surveys reveal spreading history. Drilling brings samples from beneath the sediment to study directly. Combining these methods allows scientists to see the invisible engine of the planet. The ocean floor is both stage and actor, shaping and shaped by tectonic motion. Plate tectonics under the oceans is slow but relentless. Centimeters per year add up over millions of years. Oceans grow, shrink, and rearrange. Continents drift. Deep basins form. The ocean floor carries the marks of heat, magma, and pressure, recording the cycles of creation and recycling that sustain the planet. The hidden world beneath the waves is never still. Along the mid-ocean ridges, scientists found something unexpected. In the midst of cold, dark water, streams of hot fluid rose from the seafloor. These were hydrothermal vents, a new type of system where Earth's interior met the ocean in a direct and visible way. The discovery changed understanding of the seafloor. It showed that beneath the quiet layers of sediment and rock, energy moved upward, carrying heat and chemicals from deep inside the planet. Hydrothermal systems form where water seeps into cracks in the ocean crust. Seawater penetrates deep into rock, pulled by pressure and guided by fractures. As the water moves downward, it warms from the heat of the earth. Rock near ridges is hotter because magma lies close below. Water can reach hundreds of degrees Celsius before it rises again. The path is narrow, like a hidden plumbing system, but it moves continuously. The circulating water dissolves minerals from the rock. Metals like iron, copper, and zinc are picked up as the fluid moves through hot stone. These minerals are invisible at first. They remain dissolved in the water until the fluid rises back to the cold ocean. When hot water meets cold water, minerals come out of solution. They build chimneys, some reaching tens of meters high, stacked from metal sulfides and other compounds. Each chimney is a slow-growing sculpture of chemistry. The fluid from hydrothermal vents is chemically rich. It carries hydrogen sulfide, methane, and other compounds. These chemicals form steep gradients in the water around the vents. Close to the vent, the concentration is high. Just a few meters away, it drops sharply. This steep change creates conditions that are different from the surrounding ocean. Life can take advantage of these gradients, feeding on chemical energy rather than sunlight. Energy from Earth drives the process. Heat rises from magma beneath the crust. Pressure from water above pushes it through cracks. The movement is constant, day and night. Energy is not evenly distributed. Vents can appear close together or far apart, depending on the structure of the crust and the flow of water. Each system has its own rhythm, yet all follow the same principle. Energy moves upward, altering the water and rock it encounters. Hydrothermal. Vents are temporary in geologic terms. Some last hundreds of years. Others collapse in decades. The chimneys grow as minerals precipitate, then erode as currents carry sediment. Yet even short-lived vents contribute to long-term cycles. Heat and chemicals enter the ocean. Rock changes composition. Fluid pathways remain for future circulation. The seafloor itself is reshaped by this hidden flow of energy. The vent fluids are much hotter than the surrounding water. Cold water in the deep ocean rarely exceeds 2 degrees Celsius. Hydrothermal fluids can reach 400 degrees or more. The difference drives flow. Hot water rises, cooler water replaces it. This circulation creates convection cells in the crust, moving heat and matter through kilometers of rock. The process operates quietly, invisible except for the few places where vents appear at the surface. Chemicals carried by the fluid are key to understanding seafloor processes. Metals precipitate to form chimneys. Sulfides change the local chemistry of water. Minerals can deposit in surrounding sediments. These deposits leave records of vent activity over time. By studying them, scientists can trace the movement of water through the crust, the intensity of heat, and the patterns of chemical exchange. Each deposit is a fingerprint of Earth's hidden energy. The ocean above feels the effect too. Hot fluids warm small areas of water, changing density and local flow. Chemical-rich plumes rise, mixing with cold seawater. This mixing carries metals and nutrients into surrounding ecosystems. Life is affected in ways that would not occur if the vents were absent. The energy from deep Earth drives not only mineral deposition, but also biological activity at the seafloor. Circulation patterns vary. Some water moves along cracks horizontally before rising. Other flows are nearly vertical. The paths depend on rock permeability, pressure, and the temperature gradient. Water can take hours or decades to complete a cycle. Each journey is slow compared to surface currents, yet powerful enough to alter the chemical makeup of the seafloor and the water above. Hydrothermal systems also demonstrate the connection between geology and chemistry. Magma provides heat. Water carries chemicals. Rock participates in reactions that release new compounds. Pressure controls the rate of flow. Together, these factors produce a system that moves energy from Earth's interior to the ocean in a way that is both continuous and measurable. These systems are not rare. Vents occur along ridges in every ocean, wherever magma lies close to the crust. Some regions have dense clusters, forming vent fields. Others have isolated vents separated by kilometers of rock and sediment. Even with distance, the process is similar. Water sinks, warms, dissolves minerals, and rises again. The rhythm is the same everywhere, a hidden heartbeat of the ocean floor. Heat from vents affects the seafloor structure. Rock near vents can be altered, chemically, softened, or even melted. Minerals recrystallize, filling cracks or building new structures. The seafloor is dynamic, slowly shaped by rising energy. Chimneys, mounds, and deposits record not only chemistry, but also movement, growth, and change over time. Hydrothermal systems interact with other ocean processes. Sediment layers nearby may capture minerals or fine particles carried by vent fluids. Currents distribute these materials over wide areas. Water chemistry shifts, influencing biological communities far from the source. Even though vents occupy a small area, their influence can extend for hundreds of meters or more. The hidden energy flows outward, connecting subsurface and ocean above. Scientists study vents with remote tools. Submersibles dive down, measuring temperature, chemicals, and flow. Sensors track changes over time. Samples of water and minerals are collected to understand reactions occurring beneath the seafloor. Observations reveal not only what is happening now, but also clues to past activity, stored in mineral deposits and chimney growth. The discovery of hydrothermal systems also changed ideas about life. Before, it was assumed energy for life came from sunlight. At vents, chemical energy supports ecosystems independent of light. Microbes consume sulfides, creating a base for food chains. Larger animals, such as tube worms and crabs, rely on these microbes. Life can exist in complete darkness, fed by energy rising from Earth, not the sun. Hydrothermal systems show that the seafloor is active and alive in more than one way. Heat flows, chemicals move, minerals grow, and life thrives. Energy from deep inside the planet reaches the surface and the water above. The ocean floor is not static or inert. It pulses with hidden motion, cycling matter and energy, shaping rock, water, and life simultaneously. Even where vents are absent, hydrothermal circulation leaves traces. Fluid pathways, mineralized zones, and subtle chemical shifts mark areas of past activity. The crust is porous, not solid. Water moves through it slowly. Heat and matter exchange continues invisibly. The seafloor is a network of hidden flows, connecting deep rock to the ocean above in a continuous system. This chemical and thermal exchange is part of Earth's larger balance. Energy from the mantle drives convection in the crust. Water circulation transports heat, alters rock, and provides chemical energy to ecosystems. The hidden motion beneath the seafloor shapes the entire ocean environment. Even in the quiet, dark depths, the ocean floor breathes, carrying energy upward in a slow, relentless pulse. Hydrothermal systems, though invisible most of the time, reveal a world where chemistry, heat, and motion intersect. Water moves through cracks, rock dissolves and reforms, chimneys grow, and life finds a home. The flow of energy from Earth's interior is constant. It drives change, maintains chemical gradients, and sustains ecosystems in darkness. The seafloor is a living system, powered by forces far below, quietly shaping the ocean above. Beneath the seafloor, life exists in places that seem impossible. Far below the water, within sediments and rock, microorganisms cling to small pockets of water, surviving in darkness and pressure that would crush larger life. This region is called the deep biosphere. It stretches for kilometers beneath the surface and extends across nearly all the ocean basins. Though invisible from above, it represents a hidden world filled with living cells, moving and reacting on a scale almost impossible to perceive. The organisms here are mostly microbes, bacteria, and archaea. They are small, often shaped like rods, spheres, or filaments. Each cell is measured in microns, invisible to the naked eye. They survive where energy is scarce. There is no sunlight to drive photosynthesis. Instead, they rely on chemicals found in the rock and fluids around them. Sulfates, methane, hydrogen, and minerals become fuel for metabolism. Life adapts to use what is available, however little. Metabolism in the deep biosphere is slow. These microbes divide only once every several years, decades, or even centuries. Growth is measured in millimeters over long time spans. The lack of energy keeps activity minimal. Cells exist in a near-suspended state, carrying out only essential chemical reactions to maintain themselves. The environment demands patience and efficiency. Life is not fast here. It is persistent. The sediments and rocks act as both shelter and pantry. Tiny pores between grains hold water and dissolve nutrients. Microbes move through these spaces, encountering pockets of chemicals they can use. Even rock that seems solid is porous on a microscopic scale. Channels allow fluids to flow, delivering nutrients and removing waste. Life threads through these spaces, forming a hidden network beneath the seafloor. Temperature varies with depth. In shallow sediments, temperatures may be close to the cold of the surrounding ocean, around 2 degrees Celsius. As depth increases toward the mantle, heat rises. Some microbes tolerate temperatures near the boiling point of water, adapted to extreme conditions that would destroy most other life. These thermophiles show that biology can stretch far beyond familiar boundaries. Pressure is another challenge. At a kilometer below the seafloor, pressure is hundreds of times greater than at the surface. Cell membranes, proteins, and DNA must resist compression. Microbes adapt by producing stable enzymes and protective structures. Life here is not fragile. It is resilient. It exists because it can survive conditions that would seem inhospitable from the surface. The total biomass of life in the deep biosphere is hard to measure. Estimates suggest that it may equal or exceed the total biomass of life in the ocean above, or even on land. Though individual cells are tiny, the volume they occupy is immense. Across the oceans, sediment and rock hide an enormous number of living cells, each contributing to chemical cycles and energy flow unseen. These microbes alter their environment slowly. Chemical reactions between cells and rock change mineral composition. Methane is consumed and produced. Sulfates are reduced. Elements like carbon, nitrogen, and sulfur cycle through the biosphere, connecting deep life to the larger ocean system. Even at minimal rates, these processes have a global effect over millions of years. Some microbes rely on hydrogen produced by chemical reactions in the rock. Others feed on compounds like methane or sulfides. This metabolism, independent of sunlight, is called chemosynthesis. It forms the base of a food web in places where light cannot reach. While mostly microscopic, these ecosystems can support larger life forms near fluid pathways, such as tiny worms, crustaceans, or tube-dwelling animals in sediments where chemical energy reaches the surface. Energy in the deep biosphere is limited, so growth is sparse and slow. Life exists at the threshold, surviving on a fraction of what would support surface life. Cells spend most of their existence in maintenance, not reproduction. They repair themselves, slowly replace molecules, and adjust to chemical fluctuations. Life here is not about speed or abundance, but stability and persistence. Chemical gradients guide the distribution of life. Where fluids rich in energy flow through rock, microbes cluster. Where nutrients are scarce, cells become rare and inactive. Over time, gradients shift as minerals are dissolved, fluids move, and sediment compacts. Life follows these changes, migrating through pores or adapting in place. The subsurface is dynamic, even if change occurs at geological timescales. Drilling into the seafloor provides glimpses of this hidden ecosystem. Sediment cores reveal cells alive kilometers below the surface. Fluids extracted from rock show chemical signatures of microbial activity. Scientists can sequence DNA, identify species, and understand metabolic pathways. Each sample uncovers more about a biosphere previously thought empty and silent. The deep biosphere also stores organic carbon. Microbes consume and produce compounds that affect the chemical balance of sediment and rock. In this way, life participates in Earth's carbon cycle even far below the surface. The movement of carbon through these hidden layers links deep and shallow oceans, surface ecosystems, and climate systems over long periods. Microbial activity is slow, but it is continuous. Even when growth is minimal, chemical reactions persist. Life maintains a low but steady presence, influencing minerals, gases, and fluids. Over millions of years, these processes accumulate, leaving traces that can be detected in cores and analyzed in laboratories. The deep biosphere becomes a record of both life and chemical change beneath the ocean. Despite the lack of light, the deep biosphere is diverse. Different species occupy distinct niches depending on temperature, pressure, and chemical availability. Some specialize in hydrogen oxidation, others in methane reduction, and still others in sulfur cycling. Each microbe plays a role in sustaining the ecosystem and connecting it to surrounding rock and fluid flows. Life in these depths demonstrates adaptability. Microbes endure isolation, low energy, and extreme conditions. They survive where no surface animal could. Their existence shows that biology is not confined to the world humans see. It extends deep, threading through sediments and rocks, persistent and resilient. responding to slow changes over geological time. The deep biosphere also raises questions about the total scale of life on Earth. If microbes kilometers below the ocean floor exist in such numbers, much of Earth's biomass may remain hidden. Understanding this hidden life challenges assumptions about limits, energy, and survival. It suggests that the planet harbors more living cells than once imagined, quietly shaping chemistry and energy far from sunlight. The seafloor, then, is more than a boundary between ocean and crust. It is a host to hidden ecosystems, powered not by light, but by chemistry and heat. Life threads through pores, reacts with minerals, and slowly cycles energy. It is small, slow, and largely invisible, yet vast in scale and influence. Kilometers beneath sediments and rock, the ocean floor carries a living record of persistence, adaptation, and survival in the dark. Beneath the sea floor, another hidden world exists, one built not only of rock, sediment, and life, but of frozen gas. Methane, a simple molecule composed of carbon and hydrogen, becomes trapped in ocean sediments under certain conditions. When pressure is high and temperatures are low, methane molecules combine with water to form ice-like structures called methane hydrates. These substances look solid but contain vast amounts of gas, locked in place beneath the seafloor in the dark. Methane hydrates form in specific regions of the ocean. They appear mostly along continental margins, where sediments are thick and water is deep. Depths of several hundred to a few thousand meters provide the right balance of pressure and temperature. If the water is too shallow, the structure cannot hold. If the temperature is too high, the hydrate breaks down. The sediment acts as both container and shield, keeping the gas stable for long periods. These hydrates are widespread, though not evenly distributed. Some layers extend for kilometers horizontally, forming sheets of frozen gas within the sediment. Other deposits appear as isolated pockets, trapped within porous layers. Even in small patches, the volume of methane is significant. Taken together, hydrates under the world's oceans store far more carbon than the atmosphere contains today, a hidden reservoir of chemical energy. The formation process is slow. Methane originates from the decay of organic matter or from geological reactions deep in the crust. Microbes can produce methane from buried carbon. As gas rises through sediment, it encounters conditions that favor hydrate formation. Water molecules surround the gas, creating cages that hold the methane in a solid matrix. The process requires precise environmental conditions, but occurs naturally over thousands to millions of years. Pressure is essential. As depth increases, so does the weight of water and sediment above. This weight compresses the structure, helping methane remain trapped. Temperature must remain low, near the freezing point of water. Even small changes in either factor can destabilize the hydrate. If pressure drops or temperature rises, methane is released as gas. This makes hydrates both stable and fragile, depending on their environment. Hydrates are not just frozen gas. They are part of the sedimentary system. Layers above and below interact chemically and physically with the hydrate. Sediment may compact over time, pushing against the hydrate. Water may flow through pores, delivering chemicals that slowly alter its composition. In some areas, microbial activity continues around the hydrates, consuming or producing methane, integrating the frozen deposits into the living seafloor ecosystem. Methane clathrates also influence the physical stability of the sediment. The ice-like material binds grains together. When hydrates are stable, sediments remain firm. If hydrates melt or dissociate, the sediment can weaken, causing slides or collapses. These events are rare but can reshape the seafloor rapidly, moving layers of rock and sediment in large sudden flows. Such collapses also release methane into the water above, with effects on chemistry and biology. The amount of carbon locked in these hydrates is enormous. Estimates suggest hundreds of gigatons are stored beneath the oceans, far exceeding the carbon in the atmosphere. This reservoir represents a long-term buffer, holding carbon that would otherwise circulate freely. It connects geological and biological processes, linking buried organic matter, microbial activity, and ocean chemistry in a vast, hidden cycle. Changes in the environment can threaten this balance. If water temperatures rise due to climate change, or if sediment shifts reduce pressure, hydrates may release methane. This release can feed local microbial communities, or, if large enough, contribute to the atmosphere. Because methane is a potent greenhouse gas, even partial release from hydrates has implications for global climate. The hidden reservoir beneath the seafloor is not only a record, but a potential source of rapid change. Hydrates also influence ocean chemistry. As methane dissolves in water, it reacts with oxygen and other compounds. Bacteria can oxidize the gas, producing carbon dioxide and other byproducts. These reactions shift chemical gradients in sediment and water. The process affects local biology, feeding specialized microbial communities and influencing the distribution of nutrients in the ocean above. The stability of hydrates depends on long-term geological conditions. Continents shift, currents move, and temperatures fluctuate over thousands to millions of years. Methane stored today reflects a balance maintained over these long periods. Past climate change events show that large-scale release of gas can happen naturally, though slowly, reshaping sediments and influencing the global climate system. Hydrates can also act as a source of energy for life. Microbes consume methane in situ, converting it into biomass or byproducts. This forms the base of subsurface ecosystems, connecting chemical energy to biological processes. Even frozen gas supports life, showing that the ocean floor stores energy not only in minerals and heat, but also in chemical compounds that fuel living systems far below the surface. Methane clathrates demonstrate the hidden complexity of the seafloor. They are part of an intricate web of pressure, temperature, and chemical balance. The gas is stored patiently, waiting in sediments under precise conditions. Tiny shifts can release it, sometimes gradually, sometimes more suddenly. This dual nature, as stable reservoir and potential hazard, makes the hydrate layer both fascinating and important. These deposits also act as markers of Earth's carbon cycle. Sediments preserve evidence of past methane formation and release. Layers of hydrate, mineralized residues, and chemical signals show how carbon moved between rock, sediment, water, and atmosphere over millions of years. Scientists can trace ancient methane release events, understanding both the stability of hydrates and the risks they pose for the present. In some regions, large hydrates influence seafloor topography. Ice-like layers can lift sediment slightly, forming mounds or domes. These features guide water flow, trapping sediments and affecting microbial habitats. The seafloor is molded not only by rock and tectonics, but also by the hidden pressure of trapped gas, creating subtle but measurable structures that mark the presence of carbon below. The implications extend to human concerns. Methane release from destabilized hydrates could enhance warming in the atmosphere. Underwater slides triggered by melting hydrates could affect ocean currents, sediment patterns, or even coastlines indirectly. Understanding this hidden carbon pool is essential for predicting both geological and climate risks. highlighting the connection between deep Earth processes and the world above. Despite the potential for change, hydrates persist because conditions are stable over long time spans. High pressure and low temperatures maintain the frozen gas. Sediments protect the deposits from rapid alteration. Microbial life adapts to exploit some methane, while leaving the rest untouched. The seafloor becomes a storehouse, holding carbon in balance, part of a slow and ongoing interaction between rock, water, and life. The frozen methane beneath the ocean floor is more than a chemical curiosity. It is a record of Earth's energy, a resource for life, and a factor in the stability of the planet's climate system. It demonstrates that beneath sediments and water lies a reservoir of chemical potential, shaped by pressure, temperature, and time. Even in the dark, deep below the waves, Earth stores energy and carbon in ways that connect geology, biology, and the ocean above. Methane hydrates are one of the clearest examples of how the ocean floor is active and interconnected. Heat, pressure, chemistry, and biology combine to form a hidden landscape. The carbon trapped here moves slowly, interacts with sediments and microbes, and can respond to changes in temperature or pressure. The ocean floor, once thought simple and static, reveals itself as a living archive of chemical energy and environmental balance. Beneath the oceans, where one tectonic plate meets another, the seafloor bends and sinks. These are subduction zones, regions where oceanic crust is forced down into the mantle. The descending plate carries sediments, water, and rock downward. Above it, the overriding plate resists motion. The interface between the two becomes a zone of enormous stress, locked by friction yet capable of sudden movement. The hidden interface lies deep beneath the waves, invisible to the human eye, yet it holds the potential for tremendous energy release. The plates move slowly, at rates of a few centimeters per year. This motion is imperceptible to anyone on the surface. As the oceanic plate slides beneath the continental or oceanic plate, stress accumulates along faults. In some places the rock sticks. It does not slip. The friction holds the plate in place while pressure builds. Over years, decades, and centuries, enormous force gathers quietly in these locked zones. Eventually, the stress overcomes friction. When the rock breaks or slips suddenly, the energy stored over long periods is released in a rapid movement. The result is an earthquake. Deep beneath the ocean, the fault can shift tens of meters in seconds. Water above responds immediately. The seafloor can rise or drop abruptly. Even though this happens kilometers below the surface, its effects are felt far above, across entire oceans. Megathrust earthquakes occur in the largest of these subduction zones. These quakes are the most powerful on Earth. They can release more energy in minutes than humans use in millions of years. The source lies deep, at the locked boundary between descending and overriding plates. The rupture may extend for hundreds of kilometers along the fault, a massive section of the seafloor suddenly moving. The hidden structures beneath the waves determine the size, direction, and impact of the quake. The seafloor motion can displace water, generating tsunamis. When a section of the ocean floor rises or drops suddenly, the overlying water column responds. Waves form and propagate outward at high speed, crossing oceans without losing much energy. Coastal regions far from the earthquake can experience these waves hours later. Subduction zones are therefore not just sites of hidden energy, but of direct hazard to surface populations. Even smaller, slow slips influence seismic behavior. Some parts of the fault move incrementally without causing large quakes. These slow events release energy over days or months. Though imperceptible, without instruments, They reduce or redistribute stress along the fault. They are part of a continuum of movement, from slow creep to sudden rupture. Observing these motions helps scientists understand the conditions that trigger catastrophic earthquakes. Sediment layers above the fault affect earthquake behavior. Thick, soft sediments can amplify shaking. They transmit force differently than hard rock. The composition of the descending plate influences how it bends and slips. Hydration from trapped water can lubricate the fault or create pockets of high pressure. These factors are all hidden beneath the ocean, yet they shape the size and character of earthquakes at the surface. Monitoring subduction zones requires instruments that can see through water and sediment. Seismometers detect vibrations. Pressure sensors on the seafloor detect movement. GPS measures subtle shifts of the overriding plate. By combining these tools, scientists track stress accumulation, slow slips, and potential rupture zones. Though the faults themselves remain unseen, their activity can be measured indirectly, providing insights into the processes operating below. Tsunamis, born of sudden seafloor motion, demonstrate the connection between deep structures and surface hazards. Water is displaced over wide areas. Wave height depends on how much the seafloor moves and over what distance. The shape of the seafloor guides the waves. Trenches, ridges, and continental slopes affect wave speed and height. Even small differences in the hidden landscape can change the impact on distant coastlines. Repeated earthquakes shape the seafloor itself. After large events, sections of sediment slide or collapse. Rocks fracture, and fault surfaces are reshaped. Over millennia, subduction zones develop complex structures of ridges, trenches, and fracture zones. These structures guide future earthquakes. Each event is influenced by the history of hidden motion below, showing that the seafloor records both past and potential future activity. Some earthquakes occur in unexpected locations within the subduction zone. Rock may deform within the descending plate, creating internal faults. These intraplate quakes do not release energy at the plate boundary, but still affect the seafloor and water above. The complex geometry of the subducting crust, hidden from direct observation, influences where stress concentrates and how it is released. Water within sediments affects fault behavior. Pore pressure can reduce friction, allowing the fault to slip more easily. Hydration may come from minerals in the descending plate or from sediments carried down from the ocean floor. These hidden fluids change the mechanics of earthquakes, influencing timing, magnitude, and the potential for tsunami generation. Even small pockets of water can have large effects on the system. The bending of the oceanic plate at subduction zones is a gradual but immense process. The plate descends at angles of 10 to 40 degrees, moving silently through the mantle. This bending stores energy like a compressed spring. Over millions of years, this motion builds enormous potential that can be released in seconds. The visible consequence on the surface is dramatic, yet it reflects processes occurring far below the waves. Subduction zones also link to volcanic activity. As the oceanic plate sinks, it carries water into the mantle. Water lowers the melting point of rock, generating magma that rises toward the surface. Volcanic chains, often on the overriding plate, trace these deep processes. Earthquakes and volcanoes are therefore connected through the hidden dynamics of subducting crust. The distribution of earthquakes along the fault is not uniform. Some areas remain locked for centuries. Others slip frequently in smaller events. Hidden heterogeneities in the crust, such as variations in rock type, temperature, and hydration, determine the behavior of the fault. Even minor differences at depth can influence the size and frequency of quakes at the surface. Seafloor mapping, drilling, and seismic imaging reveal only part of this hidden world. Many structures remain poorly understood. Deep faults, fractures, and sediment layers are complex, three-dimensional networks. The motion of one section can affect neighboring zones. The system operates on timescales far beyond human observation, yet it governs hazards and shapes the ocean floor. Understanding subduction zones is critical because these hidden processes affect millions of people living near coasts. Earthquakes can destroy infrastructure, tsunamis can inundate cities, and landslides can reshape islands. Yet all of these events originate from the unseen motion kilometers below the waves, demonstrating that the most powerful natural forces often occur in places humans cannot directly see. Even after earthquakes, the seafloor continues to evolve. Sediment resettles, faults adjust, and new stress accumulates. The cycle of locking, slow slip, and rupture repeats over centuries. Life on the seafloor and in overlying waters responds to these changes, adapting to subtle shifts in chemical and physical conditions. The deep ocean is alive with motion, even in silence. Subduction zones illustrate the connection between deep earth and surface events. Energy stored in hidden faults shapes coastlines, ocean currents, and ecosystems. The hidden bending, locking, and slipping of oceanic plates governs when and where disasters occur. By studying these zones, scientists uncover the mechanisms that link processes beneath the waves to hazards on land, bridging the gap between the unseen and the visible. Human beings have found ways to reach into the hidden depths beneath the ocean floor, slowly peeling back layers of sediment and rock to understand what lies beneath. Scientific drilling programs were established to explore the seafloor directly, bypassing the limits of remote sensing and sonar. Programs such as the Deep Sea Drilling Project, the Ocean Drilling Program, and the Integrated Ocean Drilling Program have sent ships equipped with drilling rigs to various oceans, extracting cores that contain thousands of meters of sediment and rock. These cores act as time capsules, preserving information about Earth's history, climate, and tectonic activity. Drilling requires careful planning. Ships must stay over the same spot for days or weeks, while a drill penetrates kilometers of sediment. The drilling is slow because the rock is dense, the water deep, and the pressures extreme. Cores are brought to the surface inside long tubes that preserve their structure. Scientists examine the layers immediately, noting differences in color, texture, and composition. Each layer tells a story of deposition, erosion, and change over time. Cores reveal the Earth's past in detail. Layers of sediment record shifts in climate, showing periods of warmer and colder oceans. Microfossils preserved in the mud indicate the types of life that existed when each layer formed. Chemical analyses show variations in carbon, oxygen, and other elements, providing clues about ocean chemistry and temperature. Sediment, thickness, composition, and structure reflect tectonic movement, sediment supply, and the influence of currents. Every meter extracted is a window into the past. The rock beneath sediments offers another perspective. Hard layers contain evidence of volcanic activity, faults, and metamorphic processes. Drilling through crust reveals magnetic and chemical patterns that indicate the age of rock and the direction it moved during seafloor spreading. The cores help scientists link distant regions of the ocean, reconstructing how plates shifted, ridges formed, and subduction zones evolved over millions of years. Despite these advances, drilling has limitations. Technology restricts the depth that can be reached. the types of rock that can be penetrated, and the precision with which cores can be preserved. Equipment must withstand extreme pressure and cold. Breakage or contamination of cores is a constant concern. Drilling is expensive, requiring specialized ships, equipment, and personnel. Operations often cost millions of dollars for a single expedition, meaning choices must be made about where to drill and what questions to prioritize. Environmental concerns also guide drilling. Disturbing sediments and rocks can release trapped gases or disrupt local ecosystems. Scientists must plan operations to minimize impact, avoiding fragile habitats or sensitive species. Protocols are in place to handle waste, prevent pollution, and respect international waters and coastal boundaries. The reach of human technology is vast, but ethical considerations shape where and how it is applied in the ocean. Cores allow scientists to study processes that occur slowly or invisibly beneath the seafloor. For example, slow accumulation of sediments, gradual movement of tectonic plates, or the long-term formation of hydrates can be observed in layers preserved over millions of years. Each core provides a snapshot of a moment in Earth's history, and when combined with other cores from different locations, a continuous record emerges, revealing patterns and trends that span oceans and continents. The drilling process itself also provides data. Sensors measure temperature, pressure, and fluid composition as the drill penetrates the seafloor, observing how rock responds to cutting, and extraction informs understanding of its physical properties and the conditions at depth. This feedback helps refine models of the crust, sediment dynamics, and fluid flow. Even the act of reaching down into the ocean contributes knowledge, demonstrating the interplay between human ingenuity and natural systems. While technology allows deep access, it is still limited compared to the vast extent of the subsurface ocean world. Most of the seafloor remains unpenetrated. Only a fraction of known sediment and rock has been cored. In many areas, conditions are too difficult, water too deep, or sediments too thick. The hidden biosphere, chemical reservoirs, and tectonic structures exist largely beyond direct reach. Scientists rely on indirect measurements, modeling, and the careful extrapolation of data from the limited cores they have obtained. Human reach is expanding slowly. Advances in drilling technology, robotics, and sensors gradually extend the limits of exploration. Autonomous vehicles and remotely operated systems allow for precise observation of the seafloor before drilling. New drilling methods penetrate deeper, maintain core integrity, and monitor conditions in real time. Yet each step comes with challenges of cost, safety, and environmental responsibility. Progress is measured, deliberate, and mindful of consequences. Ethical considerations extend to the knowledge gained as well. Understanding subsurface energy, chemical resources, and microbial life raises questions about exploitation, conservation, and stewardship. Should methane hydrates be harvested for energy? Should unique microbial ecosystems be disturbed? Human curiosity drives exploration, but responsibility shapes its application. Boundaries exist not only in technology, but in how knowledge is used and applied to benefit the planet and its inhabitants. Drilling programs also foster international collaboration. Many expeditions involve scientists from multiple countries, sharing data, cores, and expertise. Global coordination allows for comprehensive study of ocean basins, connecting findings across regions. Patterns of sedimentation, tectonics, and life emerge more clearly when cores from different oceans are compared. Human reach into the subsurface world is therefore a collective effort, linking science, technology, and collaboration. The information gained from cores informs models of Earth's processes. Sediments and rock reveal the history of ocean currents, climate change, plate motion, and chemical cycles. Methane hydrates, hydrothermal systems, and fault zones can be studied in situ. Scientists combine drilling data with sonar, seismic imaging, and remote sensing to build comprehensive models of the seafloor. Each core is a piece of a larger puzzle, connecting what is hidden below to what is observed above. Time itself is revealed in layers. Sediments accumulate slowly, each centimeter representing decades or centuries. Rock crystallizes over thousands or millions of years. Cores preserve this chronology, allowing scientists to read the Earth's history like a book. Fossils, mineral changes, chemical signatures, and structural features provide chapters in a story of oceans, plates, and life. Human drilling makes this record accessible, even if only partially. Safety is another limitation. Drilling in deep water is inherently risky. Weather, currents, and mechanical failure can endanger crews and equipment. Contingency plans are essential. Ships must be equipped to handle emergencies, and operations must follow strict protocols. Despite risks, the rewards of sampling the hidden world beneath the ocean floor drive continued exploration. In some cases, drilling uncovers surprises, unexpected layers, previously unknown minerals, or evidence of past life challenge assumptions and prompt new questions. Each expedition contributes to a growing understanding of the complexity and diversity of the seafloor environment. Human reach, though limited, continues to expand the boundaries of knowledge, slowly revealing the secrets hidden kilometers below the waves. Even as drilling technology improves, scientists recognize that much of the subsurface ocean world remains beyond human touch. Indirect measurements, modeling, and remote observation complement cores, filling gaps where direct access is impossible. This combination allows exploration without overstepping environmental, ethical, or practical boundaries, balancing curiosity with responsibility in the study of the hidden sea floor. The human presence beneath the ocean is therefore careful, measured, and purposeful. Cores are collected, data analyzed, and discoveries shared. The act of reaching into the sediment and rock allows understanding of Earth's processes, life, and chemical cycles in ways previously unimaginable. Yet each step is deliberate, acknowledging limits of technology, cost, and potential environmental impact. Knowledge grows slowly, as must human presence in this hidden world. Through these efforts, the seafloor becomes more than a remote, inaccessible region. Scientific drilling programs allow humans to touch layers that record Earth's climate, tectonic history, and hidden biosphere. Each core reveals part of a story billions of years in the making. By respecting limits and observing carefully, human reach into the subsurface ocean world transforms the unknown into knowledge, connecting the hidden depths to the surface in a slow, deliberate understanding. The ocean floor is not empty or still. It is a living system, though life here looks very different from what we see above the surface. Geology, chemistry, biology, and physics all interact in a slow, constant dance. Rock moves, sediments accumulate, fluids flow, and microorganisms live and die. Heat from the earth rises through crust and sediment, driving chemical reactions that provide energy to life. Water moves through hidden cracks, carrying minerals and nutrients. Even seemingly barren regions are part of a network of activity, connecting deep processes to the surface environment. Sediments record time. Layers of mud, sand, and tiny shells fall slowly, forming a history of climate, ocean currents, and tectonic shifts. Some sediments hold microbes that survive kilometers below, sustained by chemical energy. Hydrothermal vents carry heat and chemicals to the ocean, forming mineral structures that provide habitat for organisms independent of sunlight. Methane hydrates store carbon in frozen cages, influencing both the chemistry and the stability of the seafloor. Faults bend, break and slip, slowly releasing energy in earthquakes and shaping coastlines above. Each process feeds into the others, creating a living system that moves and changes on timescales from seconds to millions of years. The ocean floor regulates the planet in ways not immediately visible. Heat flux from the mantle affects ocean temperatures, influencing currents and climate patterns. Sediment deposition controls the cycling of carbon and other elements, linking the deep earth to the atmosphere. Microbial life transforms chemical compounds, mediating reactions that would not occur otherwise. Methane hydrates hold vast stores of carbon, stabilizing greenhouse gas levels over long periods. Even tectonic activity, while sometimes destructive, contributes to the ongoing renewal of crust, the creation of mountains, and the shaping of ocean basins. The seafloor acts as a slow, steady regulator, maintaining balance across the planet's systems. Yet much remains unknown. The vast majority of sediments and crust have not been sampled directly. Microbial communities kilometers below the surface are largely unexplored. Fluids moving through rock are only partially understood, as are the precise chemical reactions occurring in hidden layers. Even tectonic processes are measured indirectly, leaving details of fault structure, stress distribution, and long-term behavior to be inferred. For every vent studied, for every core extracted, there are hundreds of kilometers of ocean floor beyond reach, silent but active, influencing the planet in ways we have only begun to understand. The seafloor operates quietly. Energy moves upward from Earth's interior without fanfare. Minerals crystallize and dissolve. Chemical gradients form and shift. Microbes metabolize. Sediments settle. The processes are slow compared to human time, but they are continuous. They connect the deep planet to surface oceans, to the atmosphere, and to life itself. The rhythm is steady, persistent, and largely invisible. Observing it requires patience, careful measurement, and respect for the scales involved. Life is woven into every level. Microbes live in sediments, feeding on chemical energy from rock and fluid. Tube worms, crustaceans, and other creatures thrive around vents, creating localized ecosystems dependent on deep energy rather than sunlight. Even barren regions host chemical reactions and heat flow that sustain hidden communities. The seafloor demonstrates that life is not confined to the visible, illuminated world, but extends into dark, high-pressure, chemically active spaces. Geology and biology are inseparable here. Tectonic shifts reshape sediments and rock, creating pathways for fluids and habitats for life. Hydrothermal circulation alters minerals and provides energy for microbes. Faulting and subduction generate heat, stress, and movement, impacting chemistry and biology alike. The physical, chemical, and biological aspects of the ocean floor are interdependent, forming a system that responds as a whole rather than as isolated parts. The Earth's crust beneath the ocean is alive in its own quiet way. The hidden processes of the seafloor affect the planet above. Carbon stored in sediments and hydrates regulates greenhouse gas levels. Earthquakes and tsunamis reshape coastlines. Heat flow influences ocean currents. Microbial life contributes to chemical cycles that affect water quality and nutrient distribution. The activity below the waves is not separate from the surface world. It is part of a larger system that maintains the conditions necessary for life and planetary stability. Scientific exploration continues to reveal the complexity of this system. Drilling, seismic imaging, sonar mapping, and remote vehicles provide glimpses of what lies beneath. Each discovery adds depth to understanding, showing how sediments, crust, fluids, and life interact. Even as technology improves, the ocean floor remains vast, and most processes are still observed only indirectly. The hidden life and energy of the seafloor remind us of the limits of human reach, but also of the capacity for observation and understanding. The seafloor is a slow-moving archive, a dynamic habitat, a chemical reactor, and a regulator of global systems. Heat, energy, and matter circulate continuously. Life threads through pores, cracks, and fluids. Minerals form and dissolve. Sediment accumulates. Faults release energy. Each element is part of a larger system, moving at its own pace yet integrated with everything else. Time in this realm stretches beyond human perception, measured in thousands, millions, and even hundreds of millions of years, yet it unfolds steadily and predictably. There is a quiet continuity to the seafloor. Change happens constantly, but rarely abruptly. Sediments layer gently, heat flows steadily, and chemical reactions proceed slowly. Life adapts to these conditions, persisting where energy is minimal and growth is slow. Even events such as hydrothermal vent formation or fault slip are part of long cycles that integrate with surrounding processes. The seafloor demonstrates balance, resilience, and persistence, quietly maintaining connections across Earth systems. Human understanding is growing but remains partial. Each expedition, core, and observation adds to the picture, revealing complexity without revealing it all. The ocean floor is vast, continuous, and interconnected. Geology, chemistry, physics, and biology operate together to maintain a system that is both stable and dynamic. Observing it teaches not only about the seafloor itself, but about Earth as a whole, its history, its present balance, and the hidden processes that sustain it. In this living system, every process matters. The slow accumulation of sediments, the movement of tectonic plates, the flow of fluids, the metabolism of hidden microbes, and the storage of carbon all interact. Changes in one area ripple through others, showing the seafloor as a network rather than a collection of separate phenomena. Understanding these connections is essential for grasping how the planet functions over long time scales, and how seemingly invisible processes support life above. The ocean floor is both a record and a system. It records Earth's history through sediments, cores, and mineral deposits. It functions as a living system, cycling energy, heat, and chemicals. It sustains life in forms unimaginable to surface dwellers. It stabilizes climate, shapes geology, and interacts with oceans and atmosphere. Its processes are quiet, continuous, and deeply integrated, forming the foundation of planetary balance. Even as much remains unknown, the seafloor offers a model of continuity. Energy flows, matter moves, and life persists. Each process integrates with others, forming a system that is neither random nor chaotic. It is steady, resilient, and self-regulating. The hidden world beneath the ocean floor is not only a record of the past or a source of wonder. It is a living, breathing component of the Earth, quietly shaping the planet at every moment. The seafloor reminds us that activity can be profound without spectacle. Changes occur on scales beyond perception, and yet they influence the entire planet. Heat rises, fluids circulate, sediments accumulate, and microbes live. Faults slip, vents form, carbon cycles, and ecosystems endure. Together, these processes demonstrate that the ocean floor is a living system, continuously interacting with every part of Earth, quietly sustaining balance without drama or rush. We have reached the edge of current knowledge, yet even in uncertainty, there is insight. The ocean floor is a system of connections, processes, and life that operates independently of human perception. It moves, reacts, and sustains itself. It integrates geology, chemistry, biology, and physics in a continuous, seamless way. Its rhythm is subtle, steady, and unbroken. By observing, measuring, and respecting this hidden world, humans gain understanding of Earth's balance and continuity. The seafloor is alive, not in spectacle, but in its quiet, persistent work, holding the planet together beneath the waves. Humans have learned much about the ocean floor, yet the vast majority remains beyond reach. Our curiosity has led to remarkable tools: deep sea, submersibles, drilling rigs, sonar arrays, and robotic explorers. Each expedition brings new knowledge, revealing chemical cycles, tectonic activity, hidden life, and energy flows. We can observe hydrothermal vents with cameras, extract sediment cores, measure heat and pressure, and map the seafloor in detail previously unimaginable. These achievements reflect human ingenuity, but they also show how small our reach is compared to the scale of the hidden ocean world. The deeper we study, the more apparent it becomes that our actions on the surface can influence this hidden realm. Carbon emissions, climate change, ocean acidification, and pollution all affect the water column, which connects to sediments, fluids, and microbial life beneath the seafloor. Even minor changes in temperature or chemistry can ripple downward, affecting ecosystems kilometers below. The ocean floor is not isolated. It responds to the surface environment, and humans are now part of that connection. Scientific exploration is a form of stewardship. By observing and documenting the seafloor's structures, chemistry, and life, humans gain knowledge necessary for responsible interaction. Understanding how sediments trap carbon, how microbes cycle elements, and how tectonics shape the crust informs decisions about energy resources, environmental management, and climate mitigation. Careful observation allows humanity to respect the hidden systems without causing unintended damage. Yet exploration comes with boundaries. Extracting resources, disturbing sediments, or altering chemical balances can have long-term consequences. Methane hydrates, for example, store vast amounts of carbon that could affect global climate if destabilized. Drilling through sediment layers can release gases, disrupt microbial habitats, and alter local chemistry. Ethical and environmental considerations must guide every mission, balancing the pursuit of knowledge with the protection of fragile, largely unseen ecosystems. Humans are beginning to recognize that the seafloor is a partner in Earth's systems. It absorbs energy, regulates chemical cycles, and provides habitat for life that supports broader ocean ecosystems. It acts quietly, without spectacle, yet its work sustains conditions for oceans, climate, and life above. Our responsibility is to observe, understand, and minimize interference, acknowledging that hidden processes maintain a balance we depend upon. Education and collaboration extend stewardship beyond individual expeditions. International programs share data, cores, and maps. Researchers combine findings from different oceans, linking discoveries across hemispheres. Open knowledge allows better models of seafloor dynamics, revealing how energy, carbon, and life circulate. Humanity's connection to the ocean floor becomes collective, emphasizing global responsibility and shared benefit. Future exploration will require patience, careful planning, and respect for limits. Robotic systems may probe deeper, observing microbial life, heat flow, and chemical gradients without intrusive drilling. Sensors and imaging tools will allow continuous monitoring, tracking changes in real time. Each advance will reveal new connections, but it will also remind humans that the ocean floor operates on timescales far longer than human lifetimes, with processes slower and subtler than immediate observation can detect. Human presence in the subsurface ocean world is therefore an act of humility. It is not conquest, but understanding. We reach into sediments to learn about carbon storage, tectonic movement, and microbial life. But the seafloor operates independently, continuously regulating and cycling energy. By measuring, mapping, and observing, humans participate in a dialogue with a system much older and larger than ourselves, learning how to coexist with processes that have persisted for millions of years. Ultimately, the hidden ocean reminds us of continuity. Life, energy, and matter are integrated in ways that connect the deepest sediments to the surface oceans and atmosphere. Microbes metabolize, sediments accumulate, faults move, heat flows, and carbon cycles. Each component operates at its own pace, yet together they sustain a balanced system. Humanity's role is to understand, respect, and act with care, so that exploration does not disrupt the quiet work of the seafloor. The seafloor offers a perspective on patience and scale. Its hidden life moves slowly, its chemical reactions persist without attention, and its geological forces unfold over millennia. Observation allows humans to appreciate this rhythm, to see that not all important work is visible, fast, or dramatic. The ocean floor continues its tasks silently, shaping Earth systems, regulating chemistry and energy, and providing habitats for life hidden from view. It is a reminder that even the most subtle processes matter profoundly. As humans extend their reach, there is a growing responsibility to act as stewards rather than conquerors. Knowledge of the hidden ocean world is power, but it is also a duty. Understanding methane storage, deep microbial life, hydrothermal systems, and tectonic activity informs how we manage resources, predict hazards, and plan for climate change. Each expedition contributes to this knowledge while also requiring care, foresight, and ethical guidance. Exploration is most effective when it protects what it seeks to understand. In the end, the seafloor is both teacher and partner. It is a living, active, and resilient system that operates largely beyond human perception. By observing carefully, measuring continuously, and respecting the hidden processes, humans can connect to the subsurface ocean world without disrupting it. Our role is not to control, but to witness and learn, recognizing that this silent, unseen ecosystem underpins life, energy, and balance on the planet. The hidden ocean world extends far beyond what any individual expedition can touch. Sediments record millions of years, fluids circulate slowly, microbes persist in low-energy environments, and tectonic plates move with precision over vast scales. Humans glimpse this complexity through drilling, imaging, and observation. Each discovery adds to understanding, reminding us that the ocean floor is alive, integrated, and essential. It is a system in which humanity is now a participant, responsible for careful stewardship and respectful exploration. Even as many mysteries remain, the seafloor shows continuity, resilience, and connection. Life threads through sediments, heat flows through rock, chemical cycles proceed uninterrupted, and tectonics shape landscapes quietly. Observing and understanding these processes fosters a sense of respect, humility, and responsibility. Humanity's reach into this hidden world is an invitation to learn, not to dominate. The ocean floor continues its work, silently sustaining the planet, integrating geology, chemistry, physics, and life in a system of remarkable balance and quiet endurance.